All right. Hello, everybody. Let's talk about section 2.2, derivative rules. So these are some rules that generalize to all derivatives. We're now figuring out how to take derivatives quickly instead of using the laborious notation. And speaking about the laborious notation, given a function f of x, recall that f prime of x is equal to f of x plus alpha minus our f of x all over alpha. All right. So what if our function is equal to, let's say, a constant value, 7? What is f prime of x? Really, we want to know what is the derivative of a constant. Well, applying the definition, f prime of x would equal f of x plus some alpha minus some f of x all over alpha. But notice this is 7 minus 7 all over alpha, which is equal to 0 over alpha, which is equal to 0. Notice that this is true for any constant c. F of x is equal to some constant c. F prime of x is always going to equal 0 by the same steps, c minus c all over alpha, but that's 0 over alpha, which is equal to 0. So now we know always that the derivative of a constant, d dx of a constant, is equal to 0 by the above. Okay, so what about if our f of x is equal to something like this? Well, f prime of x is just equal to 0 because this is just a constant. All those fancy schmancy numbers over there, e, pi, all these huge numbers that we're talking about. Overall, this is just a ratio of two real numbers, which is a real number, and it's constant, and so it equals some c. And so when you take its derivative, it equals 0. All right. Now that we've established that, let's talk about. So this was derivative rules so far for constants. All that stuff up there. What are some derivative rules for linear functions? Okay, let's move this here. Okay, what are some derivative rules for linear functions? What if our y is x is equal to some mx plus b? All right, then d dx of y of x is equal to d dx of mx plus b. Notice when the differential operator is linear, so it transfers to both of these terms. But b is a constant, so this becomes a 0. Now, how does the derivative behave with that constant out in front? That is the question. So we don't know what's going to happen here. So let's actually find y prime of x by saying that's y of x plus alpha minus y of x all over alpha. Then once we find a general trend, we'll be able to discover what happens here. Okay. Notice that this becomes m times x plus alpha plus b minus just rmx plus b all over alpha. This equals to mx plus m alpha plus b minus mx minus b all over alpha. Cancel, 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 cancel. And so we just get m alpha all over alpha. Alphas cancel and we just get m. So it seems like this constant went to 0 and the derivative seemed to have ignored that m and just applied to x. So it seems like d dx times some m is equal to m times 1, which is just m. Why is d dx of x 1? Well, I'll show you. So what is if our f of x is equal to x, then what is f prime of x? Well, that's just dx of x. But notice that's f of x plus alpha minus f of x all over alpha. Notice that this equals x plus alpha minus x all over alpha. So these can cancel and we get alpha over alpha, which is equal to a 1. Whether alpha is positive or negative, it's always equal to a 1. So it seems like the derivative of x is just 1. That's why dx of mx plus b, which is equal to dx of mx plus dx of b, is equal to m times dx of x plus a 0, which is m times 1, which is just m. So it seems like the derivative likes to ignore constants out in front of variables. Okay? That definitely happens. So in general, this is true. dx of some c times some f of x is equal to c times dx of f of x, which we can just write this succinctly as c times f prime of x. So, for example, let's say we have f of x is equal to pi cubed x minus 1,000. What is f prime of x equal to? Well, f prime of x is equal to dx, the differential operator on this whole business here. When that differential operator transfers to each of these terms, derivative of a constant is just 0, so that goes away. And over here, the derivative ignores that constant out in front of that x. And we know ddx of x is 1, so this becomes pi cubed times 1, which is just pi cubed. Okay. This is very much like y is equal to m x plus or minus b, right? Here's another general rule. What is the dx, or the derivative of x to the n? Namely, if f of x is equal to x to the n, what is f prime of x? This is f prime of x. This guy right here is f prime of x. And so what we're about to establish is something called the power rule. The power rule. It says that ddx of x to the n is n x to the n minus 1. Let's prove such a statement, because that's quite the lofty statement. How do we know if it's true or not? Well, in mathematics, we don't accept things. We prove things. So let's prove this to be a true statement. Okay. So dx of x to the n is the same thing as f of x plus alpha minus f of x all over alpha. But that's the same thing as x plus alpha raised to the nth power minus x to the n all over alpha. What is this guy right here? What does this equal? Well, we know that we can decompose this result like so. It's called the Binomial Theorem. It says that a plus b raised to the nth power is equal to n choose k, the sum as k equals 0 to n times x to the n minus k, y to the k. What the heck does that mean? Well, notice that, for example, a plus b to the first power is just a plus b. A plus b squared is equal to a squared plus 2ab plus b squared. A plus b cubed is equal to a plus b times this a squared plus 2ab plus b squared, which then results in a cubed plus 2a squared b plus ab squared plus ba squared plus 2ab squared plus b cubed. Okay. And, you know, a plus b to the fourth power is going to be something even more extensive and more complicated. But there is a trend. Notice that there is a trend here. Let's take this down here and let's rearrange some of those terms here. Okay, notice that there's a 2 here where a squared and b is to the first power, but then there's also a 2 here when it's reversed. A is to the first power and b is squared. Furthermore, there's a 1 here and a 1 here. All right, all this relates to Pascal's triangle. Okay. If you guys are familiar to Pascal's triangle. And those are just the binomial coefficients. Okay. So what we can say is that a plus b raised to the nth power is the same thing as a to the n plus na to the n minus 1b plus n a b to the n minus 1 plus b to the n, with all these middle terms given by the binomial coefficients. So then that means this equation right here comes down to, this becomes x to the n plus n x to the n minus 1 alpha plus n x alpha to the n minus 1 plus alpha squared. And that was this piece. And so don't forget to first subtract from x to the n all over alpha. So these x to the n terms cancel. And then right here, we'll see that everything will reduce through approximations to some n x to the n minus 1 alpha all over alpha. Okay? The higher order alpha terms all go, they approximate to a lower level. So we get this right here. And we notice that the alphas cancel. And so this becomes n x to the n minus 1, which was equal to our d dx of x to the n. So you don't got to worry about all this stuff, guys. Just know that d dx of x to the n is n times x to the n minus 1. Let's use this. This seems complicated, but really, let's just apply this real quick. Here's an example. What is x to the 100? If this is f of x, what is f prime of x? Well, that's just dx of x to the 100. And that's just equal to 100 x to the 99. What about x to the 123? This is our f of x. Well, f prime of x is just 123 x to the 122. What about x to the 10? This is our f of x. Well, f prime of x is just 10x to the 9. Okay. Easy as that. Don't make it more complicated than it needs to be. All right. Now let's prove indeed that d dx of some constant times some function is equal to the constant times the derivative of the function. We noticed that that seemed to be true earlier, but we never proved it. Let's prove it. Okay, define g of x to equal c times f of x, so that g prime of x is equal to d dx of c times f of x. Okay, but that's equal to g of x plus alpha minus g of x all over alpha. Okay. Now let's utilize our definition of g of x. So this becomes c times f of x plus alpha minus c f of x all over alpha. Notice that we can factor out a c, and this becomes f of x plus alpha minus f of x. Everything divided by alpha. Notice that this is by definition equal to c times f prime of x. And so we're done. Another way to see this is to use local linearity. Another way to see it is to say, well, g prime of x is equal to g of x plus alpha minus g of x all over alpha. And recall local linearity. What does it say? It says that f of some x plus an alpha is equal to f of x plus f prime of x times your alpha. And by is equal to, what I really mean is can be approximated to. All right? And this is a very bad f. Okay. So we could utilize local linearity here to say that this is g of x plus alpha g prime of x minus g of x all over alpha. Cancel, cancel. Then you get alpha g prime of x all over alpha. Cancel out the alphas, and you just get g prime of x. Okay. So don't forget that the local linearity relationship works because you can replace it and get the same result. That's why this fact holds true. Okay. But you could also use local linearity to prove the constant can be ignored. So what I mean by this is g prime of x is the same thing as g of x plus alpha minus g of x all over alpha. This becomes the same thing as the constant c times f of x plus alpha minus the constant c f of x all over alpha. But by local linearity, we could say that this is c times f of x plus alpha f prime of x minus cf of x all over alpha. So this becomes cf of x plus c alpha f prime of x minus cf of x all over alpha. The cf of x is canceled. So this becomes c alpha f prime of x all over alpha. Cancel, cancel. So this becomes cf prime of x, which was equal to g prime of x. Let's recall that that's equal to d dx of c times f of x. So this means that the derivative ignores that constant. That's all you need to know. You don't need to know about all this stuff above here. All you need to know is that the derivative ignores constants out in front. So here's an example. What's f of x? If f of x is equal to 100 x to the second power, what's f prime of x? Well, that's dx of 100 x squared. It ignores the 100 and attacks that x squared. And then we just use the power rule. So this becomes this. Here's another example. What about f of x is equal to 3x to the 111 power? Well, f prime of x will then equal ddx of the whole thing. But it ignores the 3. So then it just becomes 3 times 111 x to the 110. So this becomes this. This is our f prime of x. Another derivative rule is sum and difference. This says that f plus or minus g of x prime, which is equal to f of x plus or minus g of x prime, is going to equal f prime of x plus or minus g prime of x. Why is this the case? Well, because ddx of f of x plus g of x is ddx of f of x plus ddx of g of x, because the differential operator is linear. So this becomes f prime of x plus g prime of x. But let's prove that. I'm just saying that this is true. Let's show it. And again, you guys don't need to know how to prove it, but you just need to know how to use it. But we'll just prove it real quick. F of x plus or minus g of x prime is equal to f of x plus alpha plus or minus g of x plus alpha. And actually, instead of saying plus or minus, we could just do it for plus. It holds for minus as well. This whole thing minus f of x plus g of x over here, all over alpha by definition of derivative. So this by local linearity is the same thing as f of x plus f prime of x alpha plus g of x plus g prime of x alpha minus f of x minus g of x all over alpha. F of x goes away, g of x goes away, so this just becomes f prime of x alpha plus g prime of x alpha over alpha. Factor out alpha. The alphas cancel, so this just becomes f prime of x plus g prime of x. And we're done. So what does this mean for you? This means for you that, okay, if my f of x is equal to 100x squared minus 2x cubed, all right, what is f prime of x? Well, f prime of x is just dx of this. And the ddx travels to both of these terms and ignores the constants out in front. Okay, so then this by the power rule just becomes 100 times 2x minus 2 times by the power rule 3x squared. So this becomes 200x minus 6x squared is equal to f prime of x. Another example is, what if our f of x is equal to x cubed plus x squared plus x plus 1? Well, f prime of x, what is that? The derivative, the differential operator, travels to each of these terms. All right, and I won't write it out explicitly, but it will travel to each of these terms. And in each case, it becomes 3x squared plus 2x plus 1 plus a 0, because the derivative of a constant is a 0. So f prime of x is 3x squared plus 2x plus 1. So what about higher order derivatives? That's not a big deal whatsoever. So what if our f of x is equal to x to the fourth? What is f double prime of x equal to? Well, f double prime of x is the same thing as d dx of d dx of f of x. Notationally, 2d dx's can be called a d squared dx squared f of x. So what does that mean in this context? Well, it just means we have a d dx of a d dx of a x to the fourth. So when the differential operator meets this term initially, it gives us a 4x cubed. And then this differential operator ignores that 4 and attacks that x cubed. And then this ends up becoming 4 times 3x squared. So combining the terms, we get this. Okay? So then this is f double prime of x. What is f quadruple prime of x? Well, take 2 more derivatives of this, d dx of d dx of 12x squared. That would just be d dx of 12 d dx of x squared. So this is just d dx of 12 times 2x, which is just d dx, put a 24 out here, of x, which is just 24 times a 1, which is just a 24. So this is equal to quadruple prime of x, the derivative quadruple prime of x. All right, moving forward. We're on page 8. Okay. Now let's talk about what is the d dx of f of x times the g of x. Many students will hypothesize that this is true, but this is not true. Okay? Actually, d dx of f of x times g of x is this, f prime of x, g of x, plus g prime of x, f of x. This is the true rule called the product rule. All right, why is this true? Let's prove it. Well, d dx of f of x, g of x. is the same thing as f of x plus alpha, g of x plus alpha, minus f of x, g of x, all over alpha. Notice that by local linearity, we can say that this is f of x plus alpha f prime of x times g of x plus alpha g prime of x minus f of x, g of x, all over alpha. Okay. So then notice that this equals f of x, g of x, minus alpha g prime of x, f of x. Plus, or this should say a plus. Okay. Plus alpha f prime of x, g of x, plus alpha squared f prime of x, g prime of x, minus this f of x, g of x term, everything divided by alpha. So the f of x, g of x terms with the minus sign go away. Then we have these two terms here. Notice that this is on a lower level than these guys, so we can approximate it away and factor out an alpha. So this is what we get. When we cancel out the alphas, we get the result that I stated above. So what does this mean for you? This means for you is that if I have some function, let's say f of x is equal to x squared times square root of x, and I ask you what is f prime of x equal to? Well, you say that f prime of x is the same thing as g of x prime h of x plus h of x prime g of x, where we say that g of x is our x squared and h of x is our square root of x. Okay. Notice that this then implies that we get a 2x here, square root of x, plus, since the square root of x is the same thing as x to the 1/2, we can use the power rule to say this is 1/2 x to the negative 1/2 times our x squared. Okay, so then this ends up becoming 2x square root of x plus x squared over 2 square root of x. Whenever you apply the definition of x to the negative 1/2, that means it's 1 over x to the positive 1/2, which means that's 1 over square root of x. And so that's why it's hanging out with the denominator, term 2. Okay. Let's do another example. What is this, 9? What about f of x is equal to cube root of x, 4th root of x? If we multiply these two guys. And what is f prime of x equal to? Well, we could say f prime of x is equal to g prime of x, h of x, plus h prime of x, g of x, where g of x is our cube root of x, and h of x is our 4th root of x. Recall that this ends up becoming x to the 1/3. This ends up becoming x to the 1/4. So then this right here is the same thing as d dx of our g, which is x to the 1/3, h of x, which is our x to the 1/4, plus d dx of our h, x to the 1/4, times our g of x, x to the 1/3. So then this ends up becoming 1/3 x to the negative 2/3, x to the 1/4, plus 1/4 x to the negative 3/4, x to the 1/3. Okay. You could leave the answer like this, or you can re-express it like so. This becomes x to the 1/4 all over 3 x to the 2/3 if you'd like. This is not necessary. I'll accept answers like this on any given day. But this is just to have you have some dexterity between the notation. All right. And clearly, we can also represent these guys as that's the same thing as the fourth root of x divided by 3 times the cube root of x squared plus this is the cube root of x all over 4 times the fourth root of x cubed. So these are all equivalent. Remember, guys, practice makes perfect. Now that we've talked about the quotient rule, let's talk. Now that we've talked about the product rule, let's talk about the quotient rule. This is the question of what is d dx of some f of x divided by some g of x. Well, it just so turns out that this is equal to bottom times derivative of the top minus the top times derivative of the bottom all over the bottom squared. Why is that? Well, we can show the quotient rule in many different ways. One way to do it is to show it via the product rule. Another way to do it is to show it via using local linearity. Okay, so here's our proof using local linearity. Well, d dx of f of x all over g of x is the same thing as f of x plus alpha all over g of x plus alpha minus f of x all over g of x, everything over alpha. Okay. But this is the same thing by local linearity as f of x plus f prime of x alpha all over g of x plus g prime of x alpha minus f of x all over g of x, everything divided by alpha. Okay. So whenever we combine, this equals everything divided by alpha. When we have everything get a common denominator, we get g of x times this whole thing, f of x plus f prime of x alpha minus g of x plus g prime of x alpha times f of x, everything divided by g of x times g of x plus g prime of x alpha. And then we'll move the calculation to another page. So bringing the calculation down here, we get g of x, f of x, plus g of x, f prime of x, alpha, minus f of x, g of x, minus f of x, g prime of x, alpha, everything divided by g of x squared plus g of x, g prime of x, alpha, everything over alpha. So when we multiply by reciprocals, this alpha comes over here. That implies we get g of x. Let's get some more room here. This implies we get g of x, f of x. And actually, why don't we do some cancellation while we can? So g of x, f of x cancel out with this. And then we can just combine the top terms succinctly. So we get g of x, f prime of x, alpha, minus f of x, g prime of x, alpha. Everything divided by alpha times the quantity g squared of x, plus g of x, g prime of x, alpha. Notice that we can factor out alpha from upstairs and cancel it out with this. So this becomes alpha times g of x, f prime of x, minus f of x, g prime of x, all over this alpha times this g squared x, plus g of x, g prime of x, alpha. Okay, canceling out the alphas and then approximating, everything with the alpha goes away. So this reduces to 0, And we just get our g of x, f prime of x minus f of x, g prime of x, all over g squared of x. And this is our dx of a ratio of f of x over g of x. Okay, so what does this mean for you? You don't have to know how to do these proofs. It might come up as an extra credit question on the test, but it's not required of you to know that stuff for this class. How do you apply this? Well, let's say we got a function f of x is equal to x cubed minus 4 divided by 2x plus 5. What is f prime of x? Well, if we say f of x is a ratio of some, let's say g of x over h of x, where this is h of x and this is g of x, we know by the quotient rule f prime of x is equal to bottom times derivative of the top minus top times derivative of the bottom all over the value of the bottom squared. So then replacing these values with what we have, h of x is just this 2x plus 5. G prime of x is the derivative of this guy. So that's just 3x squared minus g of x is this guy. That's just x cubed minus 4 times h prime of x, which is the derivative of this, which is 2, all over the bottom, this 2x plus 5 quantity squared. And you're done. This is it. Here's another example. Let's say you have f of x is equal to 4x squared minus 7x plus 8, x to the 5th plus x cubed. All right, and we want to know what is f prime of x. Again, say f of x is some g of x over some h of x, where this is g and this is h. We know that that implies f prime of x is equal to the bottom h times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, so h of x is the denominator fraction, or it's the denominator function. So this becomes x to the 5th plus x cubed times g prime of x. So g prime of x is the numerator derivative. So this becomes a 8x minus 7 minus g of x. What was g of x? It's just this 4x squared minus 7x plus 8 multiplied times what is h prime of x? H prime of x is this thing taking the derivative of this thing. So this becomes 5x to the 4th plus 3x squared. Everything divided by h of x squared. There you go. This is equal to f prime of x. That's how you utilize the quotient rule. All right. So what about d dx of x to the n if n is negative? So for example, what is the d dx of x to the negative 13 equal to? Quite simply, that's just equal to negative 13 x to the negative 14, because it's still adhering to the power rule, where you bring the power down and you subtract that power by 1. We brought the power down and subtracted negative 13 by 1, which gives us negative 14. So for example, what is the dx of, let's say, negative x to the negative 1/2? So then that's equal to negative 1/2 x to the negative 1/2 minus a 1. Notice that when you get a common denominator, that's negative 1/2 minus 2 over 2. So that's negative 3/2. So this becomes 1/2 because the negatives cancel. x to the negative 3/2. Okay. Here's another example. What's d dx of 3x to the negative 3? So notice the derivative, the differential operator ignores this constant. It just attacks this x to the negative 3. So this becomes 3 times a negative 3, x to the negative 4. Easy as that. So this becomes negative 9, x to the negative 4. Okay. Very good. This concludes and wraps up 2.2, our section on our differentiability rules.